Welcome to lecture 39 on essentials of topology. In this lecture 2, we will continue the study of the concept of connectedness. Specifically, we will study the connectedness of set of reals and its subsets. Begin with, whenever we are looking for the connectedness of R, note that on set of real numbers, we have seen a number of topologies. Even we have seen that with respect to lower limit topology, this space is disconnected. We have also seen that if we are taking real line with Euclidean topology, Q as a subset of R, that is set of rationals, we have seen that this is disconnected. Till now, we have not discussed about the connectedness of this R with Euclidean topology. So, first our motive will be to discuss the connectedness of this topological space, and after that we will see that what are the subsets of R which will also be connected. At least we have seen that this set of rational numbers is not connected, but we will focus on the connected subsets of R. Moving ahead, what we will show that this set of real numbers along with Euclidean topology is connected. In order to prove this result, we require two fundamental notions which are well known in the theory of real numbers. The first one is, if the subset of R that is bounded above has a least upper bound, and this least upper bound is also known as supremum, and this is known as the least upper bound property. Also, the second one, if we are taking two real numbers x and y with x is less than y, then there exists a real number z such that x is less than z less than y. With these two fundamental concepts, let us show that R along with Euclidean topology is connected. We will prove it by contradiction. So, if possible, let us assume that this topological space R with Euclidean topology be disconnected. Now, if it is disconnected, then by the definition of disconnectedness, there exists two subsets A and B of this set of real numbers such that these are non-empty. These A and B are open. They are also disjoint, and their union is the set of reals, that is R. Now, as A and B are non-empty, we can take a real number in A and the real number in B. Note that as A and B are real numbers, either A is less than B, or A is equal to B, or A is greater than B. But it is to be noted that A and B are disjoint, so A cannot be equal to B. Therefore, either A is less than B or A is greater than B. So, we are discussing for only one case, A and B can be interchanged. So, if we are taking A is less than B, what we can discuss, let us take this is the real line. This is real number A and this is the real number B. Now, we can talk about this closed interval AB. Now let us construct some subsets of this AB by choosing. Let us take this AB intersection A. Let us name it as A naught, and similarly if we are taking this closed interval AB intersection B, let us take this is B naught. This A naught and B naught have some features, and the features are, first things, A naught and B naught both are non-empty because A is the member of this intersection and B is the member of this intersection. Also, this A naught and B naught are open sets with respect to relative topology on this closed interval AB. So we are writing these are open sets in this closed interval AB. Further, if we are taking their intersection, so this intersection will be equal to A and B intersection A intersection B. But note that A and B are disjoint, therefore A naught and B naught will also be disjoint. Now, if we are taking their union, so A naught union B naught, this is union of this closed interval intersection A union this closed interval intersection B, and it can be written as this closed interval AB intersection A union B, but note that A union B is R, therefore this is precisely closed interval AB. Thus, what we have seen, if real line with this Euclidean topology is disconnected, we can also create a separation of this closed interval AB, and that separation is given by this pair A naught B naught. Moving ahead, as we have taken A belongs to A, and it is to be noted that this A is open with respect to this Euclidean topology. Therefore, we can say that this semi-open interval A plus epsilon, epsilon is greater than 0, is contained in this set A. Even if we are choosing some small epsilon, we can also say that this is a subset of A intersection this closed interval AB, which is nothing but A naught. Similarly, as B belongs to B and B is also open with respect to Euclidean topology, there exists, if we are taking that epsilon, we can say that this B minus epsilon and this B, so this semi-open interval is subset of B, and again if we are choosing that small epsilon, then this is B intersection AB, and which is nothing but equal to B naught. What exactly we are talking, that on this real line, if we are taking this is A and this is B, note that this A is a member of A, and if this is a member of A, so this structure will be something like this one, and if this structure is something like this one, what we can say that by using the definition of this Euclidean topology, we can construct an interval of this form which is subset of A, and this will also contain in closed interval AB. Similarly, we can talk about this B as well as this open set B. Also, if we see the structure of this closed interval AB, we have seen that A naught union B naught is equal to this closed interval AB. Meaning is that this A naught is a subset of AB, and if A naught is a subset of AB, we can say that this is bounded above. And if this is bounded above, and therefore by using the least upper bound property, there exists a supremum of this set. Let us take the supremum is this C. So exactly what we are taking the supremum of A naught as C. Also, as A naught is a subset of this closed interval AB, we can say that this C will always lie between A to B. Now what we can observe? We can observe that this C will always be greater than or equal to A plus epsilon, and this is less than or equal to B minus epsilon. Question is why? Answer is just C. What C is? C is supremum of A naught, and A naught is superset of this interval. And what is the supremum of this interval? That is A plus epsilon. Therefore, this C will always be greater than or equal to A plus epsilon. Now, coming to this part, how C is less than or equal to B minus epsilon. Note that if we are taking any x belongs to A naught, question is whether this x is greater than B minus epsilon. Answer is no. Why? Because if this x is greater than B minus epsilon, then by using this concept, what will happen? This x belongs to this B minus epsilon B, which is subset of B naught, that is x will be member of B naught. But what we have seen, A naught and B naught are disjoint. Therefore, this is a contradiction. It means that none of the element of this set, that is A naught, can be greater than B minus epsilon. That is, B minus epsilon is an upper bound of A naught, and that's why this is greater than or equal to the least upper bound, that is supremum of A naught. Finally, what we have with us, note that this C belongs to closed interval AB, which is equal to A naught union B naught. What we can show that C is neither an element of A naught and C cannot be member of B naught. If we can justify these two, then from here we will reach to a contradiction, and after that we can conclude that this topological space is connected. So finally we are going to justify that C is neither an element of A naught and C is not element of B naught. Now if C is an element of A naught, which is precisely the intersection of AB with A, so C is also an element of this set A. Note that this A is open. Therefore, as we have discussed here, we can find out some epsilon or some delta greater than 0 such that this semi-open interval C plus delta is a subset of A, and not only A. This is A along with intersection or A intersection AB, which is nothing but A naught. Now, if this is an or this is a subset of A naught, it is to be noted that what about C plus delta by 2? This is a member of this semi-open interval, and this semi-open interval is a subset of A naught. It means that C plus delta by 2 is an element of A naught, and this is strictly greater than C. But what we have taken? This C was supremum of A naught. But in A naught itself, we have got a member which is greater than C. So this is a contradiction. Therefore, what we can conclude that C cannot be element of A naught. Now, if we are taking C as a member of this B naught, and B naught is nothing but intersection of this closed interval AB with B. It means that C is an element of this B, and what is this B? B is an open set. So, similar to the justification, what we have done here, what we can conclude that there exists some delta dash greater than 0 such that this C minus delta dash C, this is a subset of B intersection AB, and which is nothing but B naught. Now, if this is a subset of B naught, let us think about C minus delta dash by 2. This is a member of this semi-open interval C minus delta dash C, which is subset of B naught, or we can conclude that C minus delta dash by 2 is a member of B naught. As we have justified here that this B minus epsilon is an upper bound of A naught, in the same line what we can say that this C minus delta dash by 2 is an upper bound of A naught, but note that C is the least upper bound, and what we have with us, this C minus delta dash by 2 is strictly less than C. Again we reach to a contradiction. Thus in this case too, C cannot be element of B naught. So we have shown that C is neither an element of A naught, C is not element of B naught, while as per our construction, C was a member of this interval, and this interval was union of two disjoint open sets A naught and B naught. So finally we have shown the contradiction, and therefore this real line with Euclidean topology is connected. Having this knowledge that real line with Euclidean topology is connected, we can talk about the connectedness of Rn with standard topology or Euclidean topology on it, that we can say that product topology, and it follows from the fact that, which we have already studied, that if we are having these topological spaces x1 tau 1, x2 tau 2 and xn tau n, then if these are connected, their product, that is x1 cross x2 cross xn with the product topology, this is also connected. As we have already justified that real line with Euclidean topology is connected, therefore Rn with Euclidean topology is also connected. Moving ahead, what we can justify by using the fact that this real line with Euclidean topology is connected, all the intervals are also connected. Even if we are beginning with the singleton set A, where A is a real number, note that the singleton set A can be visualized as this closed interval A, and we know that singleton sets are always connected, therefore this is connected. Now if we are taking this open interval AB where A is less than B and A and B are real numbers, we have already seen that this open interval AB is homeomorphic to R, and if this is homeomorphic to R, we have already seen that connectedness is topological property. Because this real line with Euclidean topology is connected, we can say that this open interval AB is connected. Moving ahead, also we know that if a set is connected, its closure is also connected. So, as this open interval AB is connected, the closure of this set is closed interval AB. So, we can conclude that this closed interval AB is also connected. Also, we know that this AB is subset of this semi-open interval AB, and this open interval AB is also a subset of this semi-open interval 2, and these are subsets of this closed interval AB. This closed interval AB is nothing but the closure of this open interval AB. Therefore, we can also conclude that these semi-open intervals, that is, this interval as well as this interval, are also connected. Moving ahead, we have also shown that this A to infinity, this interval is homeomorphic to R. And again, with the same justification, we can say that this is a connected set. Now, if this is connected, what about its closure? Its closure is nothing but this interval. This is the closure of the interval A to infinity. Therefore, this is also connected. Finally, as this interval A to infinity is homeomorphic to this minus infinity to A, meaning is that the intervals of this form is also connected. Or we can say that the intervals infinity or minus infinity to A, this is connected. And if this is connected, what about its closure? If we are taking the closure of this interval, that is nothing but minus infinity to the interval which is closed at A, this is also connected. So what we have shown that by using the connectedness of real line with Euclidean topology, all the intervals are also connected. Moving ahead, even what we can justify that only connected subsets or connected subsets of R are only interval. That is, if we are taking any subset of A, or if we are taking a subset A of R, if this is not interval, then what will happen? This is disconnected. Let us justify this statement that if A subset of R is connected, then A is an interval. So let us assume that A is connected. Now let us assume that if possible, let this A be not an interval. A be not an interval. Also take two real numbers A and B in A and assume that A is less than B. Because A is not an interval, what we can say that there exists a real number x such that A is less than x less than B, and note that x is not member of A. Now what we can do? If we are looking towards the real line, our motive is, or what we have taken, this is x, this is a real number A, and this is a real number B. Now let us consider this portion of real line which is minus infinity to x, and another portion of this real line, that is x to infinity. That is, we are taking this interval minus infinity to x as well as x to infinity. Note that both are tau e open. Now let us take a naught as a intersection this interval minus infinity to x and b naught as this interval or this set a intersection with the interval x to infinity. Note that a naught and b naught both are non-empty because a is a member of a naught and b is a member of b naught, which is clear from here. Also, this a naught and b naught are open in A, as we can visualize A as a subspace of this real line with Euclidean topology. If we are looking for the intersection of A naught and B naught, from here this is clear that this is empty, that is A naught and B naught are disjoint. And finally, if we are computing the union of A naught and B naught, that is precisely A intersection minus infinity to x union A intersection this interval x to infinity, and that will always be equal to A. Thus, what we have done, we have created a separation which is a pair A naught B naught. This is a separation of the set A. But note that we have already assumed that A is connected, so this is a contradiction, and we reached to this contradiction because we have assumed that A is not an interval, hence A is an interval. These are the references for the lecture. That's all from this lecture. Thank you.